Hello everyone, my name is Hafiz and today I'll be presenting our work on adapt but don't forget fine-tuning and contrastive routing for lane detection under distribution shift. So what happens when there is a distribution shift in machine learning? Let's say we have an ML model which is trained on a distribution A initially, and let's assume we have a new incoming distribution during deployment called B. When we test our model on this new distribution, we observe that the performance degrades, and this is due to the phenomenon of distribution shift. Now, what's the problem with naively going ahead and fine-tuning the model on B? Well, we observe that the model faces catastrophic forgetting, meaning it loses performance on the prior learned data. We study this problem especially in the area of lane detection, where there are different data sets called CU lane, curve lanes. These are the car lane data sets captured in different environments and settings. And also we have the SS taxi data set, which consists of taxiways and runway line markings. Giving you a slight overview of state-of-the-art lane detection model. In our research, we use CLRERNet as a case study where it has different components which capture different aspects of for segmenting a lane marking. It begins with a strong backbone like ResNet to extract hierarchical visual features from the input image. These low and mid-level features capture lane structure, texture, and context necessary for localization. Next, moving on to the head, these features are passed through a feature pyramid network style neck that fuses multi-scale representation so that the model can reason about both global road geometry and find local details. Finally, the detection head operates in a row-wise anchor-based fashion. It starts with a set of lane priors and iteratively refines them across multiple feature pyramid levels. At each stage, features are sampled along these lane anchors, refined via cross-attention with the global feature map, and updated through regression and classification heads. So as we saw the different components of the model, what could a simple solution be if we just train the model for every new incoming distribution and have a simple classification model route those inputs to the corresponding model's branches? The parameters would increase linearly with the new incoming distributions, right? So what we do is go ahead and decompose the model into these different components of backbone, neck, and head and try to study the retention and adaptation trade-off and basically fine-tune hierarchically, starting from the deepest level of the model where we fine-tune only the bias terms of head and neck, and then the head and neck, and then basically the different components here. And as we do this, when we use the car lane data sets as the initial distribution, we see that the neck plus head fine-tuning provides a good level of adaptation on these incoming distributions with few parameters compared to using all the components of the model. Now, when we use SS taxi, which is a taxiways and runways data set, we observe that a more number of parameters are required for fine-tuning, which is using also the backbone's last two layers, since it has lesser features, the SS taxi data set. So once we identified that, can we now just clone and fine-tune only the necessary components? Well, yes, but there's still one more problem to address. We now require a classifier that can route the input features to the corresponding model's branch. So as we see here, the features on the left image, the leftmost image are entangled. And to disentangle them, we basically train a classification model using supervised contrastive loss, which clusters them nicely. And on the right side, we see the features extracted from an untrained model versus a trained model of the supervised contrastive learning. And now moving on, our proposed architecture is basically training initially on, let's say if we are dealing with car lane data sets, we train the model end to end with the backbone, neck, and head updated. Now, when we have the new incoming distributions, the curve length and SS taxi, we freeze the backbone and fine-tune only the neck and head components. And in the step 4, we train the classification model using supervised contrastive loss. During inference, the input is passed through the shared backbone now, and those features are routed through the corresponding model's branches using centroid-based classification from our supervised contrastive learned model. Well, when we have now SS taxi as the initial distribution, we see that a more deeper level of and more number of parameters are required to be fine-tuned. So we now freeze only the top 3 layers of backbone and fine-tune the bottom 2 layers and the neck and head. And similarly, the inference happens now after the top 3 layers of the backbone. Now looking at the results, the CU lane and curve lanes routing occurs at neck plus head, where only 41% of parameters are used, whereas when SSTAC-C is used, 96% of parameters are used. In both cases, we save up on parameters, providing a good level of performance across all three datasets. Thank you.